So today should be quite a nice, short and sweet integration. I'm going to recap a lot of the year 12 stuff and introduce you to some year 13 content as well, now that all year 13s are finished. So some of the integration that you'll already know from year 12 is obviously the power rule. So x to the n will integrate to x to the n plus 1 divided by n plus 1. Some of the ones that we covered in the last differentiation session last week are 1 over x, which will integrate to ln x, and then the integrals of sine and cos as well. Then there's everybody's favourite, the integral of e to the x, which just stays as e to the x. So we'll have a look at some of practice questions just using these. So we've got quite a few terms here, which we can just integrate each of them separately. This would be, how many terms we've got? 1, 2, 3, 4, 5, 6. It would be 6 marks on an exam paper. So it is worth the effort to integrate each one by itself. So the first one is a nice power rule. Then we've got a 7 over x on that last page. 1 over x integrates to ln x, and then we can leave our constant of 7 there. We've got integrals of sine and cos, and then the easy one at the end, e to the x. The extra little mark that will always get an integration is that plus c. So remember to add your constant on the end. It's always the easiest mark to get, and the easiest mark to forget as well. The next one we'll have a look at, 3 over x to the 5 plus 7 plus 3 over the square root of x plus 3 sine x. So we've got a few more tricky things in there. The 3 over x to the 5 is probably easiest to write as 3x to the minus 5, and then you can just use your power rule then to integrate it. Same with the 3 over the square root of x. We can rewrite that as 3x to the minus a half, and then it's exactly the same. So you should get that for that second one, and then obviously remember your plus c on the end too. So they were my first nice 2 examples. The next ones we'll look at some definite integrals. So these just have limits. So we just want to calculate the value of this integral between 1 and 3. So it's just a little bit more work at the end to put those limits in. So we should be able to integrate the 3 over x to the 4 minus 3 over x plus e to the x over 3. And we'll get minus 1 over x cubed minus 3 ln x plus e to the x over 3. And then finally, we just want to put our limits in there. So when you put in the limits in the first one, we'll put 3, and then we'll take away the second one when x equals 1. And that's what we should have for that one. The tricky part here is leaving your answer in exact form. So if there's anything horrible like logarithms or exponentials that we've got here, we want to leave it in that exact form. A lot of people confuse this with exact being a decimal form, which is not an exact form. So we want to leave that in all the lovely things of logs and exponentials. So I'll just collect a few terms together. The constants, the logs, I'll collect together. ln1 equals 0. That makes that a bit easier. And then the exponentials I'll put together. So I think that's probably the nicest way that one will go. Other than that, we can't do too much to it. So that's the nicest that one will look. This one goes much nicer though. So this is the integral between 0 and pi over 2. Now we've got a pi in there. Remember, you're in radians. So when we're putting the limits in, just make sure you calculate it in radians. And we've got the integral of sine x plus cos x. It's quite a memory test to remember which one differentiates to which, or integrates to which. So sine x integrates to minus cos, and cos x integrates to sine. And then we'll just do the exact same again and put those limits in. So if you put pi over 2 into the first bucket and 0 into the next one. A lot of those values go quite nice. You just get a few 1s and 0s out, and we get our nice answer of just 2. So that did go a lot easier. The next one, I want to build on some things that you've been doing in year 12, make it a little bit more difficult. And we're going to look at some integration by substitution. So if we want to integrate quite a big polynomial, so you don't want to expand all of that because it's to the power of 5, you can do if you really want, and then just use your power rule for everything. There's a nicer way of doing it. So in this method, we'll let u equal that part in the bracket, so 3x minus 7. An easy thing to do, if we differentiate u with respect to x, we get a 3. So if I rearrange that for dx, I get 1/3 times du. And I'm going to change all of this equation and just write it in terms of u. So that's why I wanted to rearrange it for dx. So now dx is 1/3 du. So all of that equation in terms of u, I've got my u to the power of 5, which is my 3x minus 7 to the power of 5. And then I've got my dx, my third, which I've just put at the front, and the du, which I've left at the end. This is much nicer to integrate, a third u to the 5 du. So we're integrating that in terms of u. So u to the 5 will integrate to u to the 6 over 6. You can leave that third out as a constant. If I simplify that a little bit, we've got u to the 6 plus 18. And then finally, I can just sub back in what I had for u. So u was 3x minus 7. So if I put that back in, remember my plus c constant on the end, then it's a much nicer way to integrate that whole function. So we'll try a similar one, a fancy one, where we're going to integrate sine of 5x minus 7. So it's that 5x minus 7 that I don't like at the moment, so we'll let that part be u. And we'll just work out du by dx and then rearrange that for dx. So du by dx is a nice one to differentiate. Rearrange that for dx, we get 1/5 du. So I'll try and just write that sine of 5x minus 7 dx, all in terms of u. So we've got sine u and then 1/5 and du. And then that's much nicer to integrate them. So that 5th I can leave out as a constant. Sine integrates to minus cos. And then we can just sub back what we had for u and to leave it in terms of x. If we look at, I'll consider more of a general case because this is a little bit easier because you'll have to integrate these so much over the next few months or the next year. It might be easier to just make a formula for it and then you can use that. So if we have cos of something x plus b and we want to integrate that in terms of x, we'd let u be the part that's in the bracket, so ax plus b. So then du by dx is just a if we differentiated that. And if I rearrange that for dx, I'd have 1 over a times du. So if I try the same thing again, just rewriting all of that in terms of u, I've took that 1 over a out at the start as my constant. Cos will integrate to sine, and then finally we can put it back in the form, back in terms of x as well. So it might be a nicer one to kind of remember so that you don't have to go through 5 different steps each time. So the integral of cos of ax plus b will always go to 1 over a times by sine of ax plus b. And then remember your plus c on the end. So you can make a really similar one for the integral of sine of ax plus b. And it might be nice to just put a few of these on flashcards so that you don't have to go through all the steps every time. Save save you a bit of time in the exam. So if you've seen something like this, cos of 7x minus 5, using what we've just done on the last one, we know it's cos integrated to a sine, and we know that that constant, well, the 7 from the derivative of 7x minus 5 will just go underneath it. So we've got 1/7 of sine of 7x plus minus 5, and then plus that constant c on the end. So it's a bit nicer if we have a few formulas for the integrals of these sine and cos ones. It might save you a bit of time in calculating it. The next thing that will be slightly new is called integration by parts. So you may have seen this formula before, and I'm going to show you a couple of examples in using this formula. So if we want to calculate the integral of u dv by dx, so in terms of x, then using this formula, that's u times v minus the integral of v times du by dx. So if we have some integral that we want to calculate, and it's kind of in two parts, we can call one part u, and we can call the other part dv by dx. And then we can use this nice formula to integrate it this way. So I think the best way to explain this is through an example. So we'll look at this one, the integral of x cos x dx. So x times cos x in terms of x. So one has to be u, the other has to be dv by dx. So we'll go u equals our first one x, dv by dx equals cos x. And then in that formula, we just need to work out du by dx and v. So du by dx, if we differentiate u, we'll just get 1. That's a really nice one. And to work out v, we just need to integrate dv by dx. So if we integrate cos, then we'll get sine. And then we can put it all into the formula. So that was the integral of u times dv by dx equals u times v, which is now sine x, minus the integral of v times by du by dx, which is really nice because that du by dx is just 1. This is why it's integration by parts, because we've done some of it. We've got another integral that we need to calculate before we'll have our final answer. But it gets easier from here. So the integral of sine x is minus cos, and then we can just simplify that a little bit. We've got x sine x plus cos x, and then plus our constant of integration c. So there is a little bit more work in these ones, but you'd usually use integration by parts when you've got two things timed together. I'll show you one final example, which is a little bit trickier because it's a natural log, which nobody tends to like natural logarithms anyway. But I'll show you how to integrate this one because we know how to differentiate it. It's nice and easy to differentiate, and it just goes to 1 over x. But integrating it is a lot more difficult. So we'll use integration by parts using we usually let one function be u, so I'll let ln x be u, and we let another function be dv by dx, but we don't have anything else in this one. So I'll imagine that this ln x is just ln x times by 1. So if we go our first function ln x and then dv by dx equals 1, then we'll try and use integration by parts. So du by dx, if I differentiate ln x, I'll get 1 over x. And if dv by dx is 1, to work out v, I need to integrate dv by dx. And the integral of 1 in terms of x is just x. So I've got my u, my dv by dx, my du by dx, and the v. And then we can put it all into the formula. that formula from with u times, u being ln x, times v, which is now just x. I just put that at the front, minus the integral of v times du by dx. So v is x, and du by dx is 1 over x, which makes it much nicer. We've got the integral of x over x, but that's just the integral of 1, and the integral of 1 in terms of x is just x. So the integral of ln x altogether is x ln x minus x, and then plus our constant of integration c. So we've got the derivative of ln x is, as it's just 1 over x, is much easier than doing that integration of ln x. But you can use integration by parts, which should make it a little bit nicer. So I've gone through probably quite some horrible examples. Integration by substitution, integration by parts. Another thing that you'll meet in the next year is integration using partial fractions. Partial fractions is one of the topics that you'll do at the very start of year 13, probably. So pay attention there, because they'll put loads of integration in that and just make it a little bit worse. But I'm sure there's some horrible examples that I've gone through, and I'm happy to go back through whatever you found was the worst one. But thank you for listening, and I'd love to, if anyone has any questions, we'll go over some more.
That's great, Rhian. Thank you so much for that. We haven't had any questions just yet, but there still is time. So if you do have any, yeah, just pop them into the chat if you do have any. Meanwhile, I'm just going to drop a few links into the chat. I have just dropped in a evaluation form that would be really useful and helpful if you could fill that in. It's not compulsory to fill it in, but as I said, it's just a link to an evaluation form that will be helpful for us. And I'll also pop into the chat, if that's okay with you, Rhian, the workbook solutions and answers.
Yeah, that'd be perfect. You're allowed the answers now.
Yeah.
Just a little bit extra in that workbook as well. I've just put a nice little example of partial fractions and integration in that, which takes a bit longer to go over all the partial fractions as well. But I added it into the notes, so there's a nice example there for you too.
Brilliant, that's great. So I've just put that in now, so that's gone into the chat. And I think that is all from us. Just quickly double check we don't have any more questions that have come through. No, that's all.
That as a good thing.
Sorry, I didn't hear that, Rhian.
I'll take that as a good thing.
Yeah.
Silence.
That's great. Well, thank you so much, everyone. We hope you've enjoyed this series of Maths Boost revision sessions. Hopefully you found it all useful. And if there is anything else we can help you with, then please take a look at our outreach page on the University of Chester's website, where you'll be able to find all of our resources, including videos of these Maths Boost revision sessions and information about our next events. Thank you again so much, Rhian, for that. Thank you very much, everyone, and we hope to see you again soon. Thank you.
Thank you.